to Statistics for Business Research, BUS 819D. Okay, today we are going to look at measure of relationships, and under that we are going to look at correlation coefficient and also look at sample regression. We will start with correlation, and under this correlation we are going to look at Pearson's product moment correlation coefficient, normally called Pearson R for sample correlation or rho for population correlation. Now, when we say correlation, it's a measure of association, a linear association between two numeric variables, say x and y. So in simple, we say correlation measures the strength of linear association between two numeric variables, x and y. The association look at the strength, then also indicate the direction of the association, and that one is indicated by the sign of the correlation coefficient. The correlation coefficient is a unitless quantity. It has no unit, and it ranges from -1 to +1. So it means that your correlation coefficient should always fall within the ranges of within the bounds or the range of -1 to +1. So when you are doing your analysis and you are getting correlation coefficient more than 1 or less than -1, then it means that there's something wrong with your calculation. Correlation cannot go beyond the -1 and +1 bound. And if your correlation coefficient is less than 0, meaning that it's a negative association. So when you have a correlation coefficient to be less than 0, it means that there is a negative association between the two quantities you are dealing with. So if it's s and y, it means that there's a negative association between s and y. And the implication is that as s increases, y generally decreases. And if your r or your correlation coefficient is greater than 0, then there is a positive association between x and y. And the indication is that as s increases, y generally increases, meaning they both move in the same direction. Now, if you come to our daily life activities, we can use the issue of temperature increase and the consumption of water. You realize that when temperature or the weather is warm or temperature increases, people tend to consume a lot of water. That's an indication of a positive association. So the quantity of water consumed increases as temperature also increases. So there's a positive association. But if you compare between temperature and, say, alcohol, you realize that consumption of alcohol decreases as temperature increases. When the weather becomes too hot, people tend to consume less alcohol. And there are some other indicators too that we can also look at between price and demand. You see there's a negative association. As price increases, generally you see demand for a commodity also decrease. So there's a negative association there. But supply and price are positively correlated, or it means that there's a positive association between. As the price increases, producers tend to supply more because they want to make more gains. Now, when your R is getting closer to 0, then the association becomes weaker. So when the correlation coefficient is close to 0, the implication is that the linear association between the two quantities, say x and y, is very weak. It does not mean that there's no association. In fact, let me emphasize this, that the correlation measures association, linear association, not just relationships. It's a linear association. So when correlation coefficient is 0, it does not mean that there's no relationship between the two quantities, but just that there's no linear association between the two quantities. Because it could be that the relationship is curvilinear, or it could be non-linear, and in that case the Pearson correlation coefficient will not be able to detect such relationships and could report that the correlation coefficient there is 0. So you have to bear in mind, you have to take note of this issue, that correlation coefficient, Pearson correlation coefficient, measures linear association between x and y, but not just association. And as we indicated, we have some scale. For example, if you look at the scale here, you see that when your correlation coefficient is within the ranges of 0 is less than the magnitude of 0.2, then we say that there is a weak correlation between the two quantities. So here it falls within the ranges of 0 and 1. It doesn't matter whether it's negative or positive. The sign is not important. So if it is negative 1, you only take the absolute value, and then becomes 1, 0.1 if it is negative. So we are looking at the magnitude of it here. The same way, if your correlation coefficient is within 0.2, less or probably equal to r, and r is less or equal to 0.5, then you will say that it's mild. It's mild. So we are looking at, so if you have, say, negative 0.4, it's a negative association and mild. And then you have moderate, which is about 0.5, and less than 0.8. So we say that this one is a moderate relationship between the two quantities. And if you have 0.8 R and above to 0.21, then we say that the correlation coefficient here is strong. So for example, if the correlation coefficient between x and y is equal to negative 0.75, the absolute value of this, the absolute value of x and y is equal to 0.75. So it will fall within here, the range here, which we will say that is a moderate. And that moderate, but the sign here is negative, so it means that it's a negative moderate correlation between x and y. Again, there are some other classifications, because in most cases the correlation, when we are interpreting correlation, we base them on existing literature. Now if you look at Cohen 1998, he also came out with some classification. So in most cases, when you are dealing with correlation and you are interpreting them, you need to interpret them in context. You need to indicate based on whose classification you are looking at. Okay, generally we can just indicate whether it's strong, weak, or very strong, but it is essential that when you are dealing with correlation, you indicate the classification you are using based on existing literature. So for example, Cohen 1998 came with a classification which indicate that a correlation coefficient between 0.1 less or equal to 0.3 is seen as very weak. very weak. Then from negative 3 to between 3 to 0.9, that is 0.3 less or equal to 0.5, meaning it is within the ranges of negative 3, 0.3 inclusive, 0.3 inclusive, then to 0.5 exclusive. So we can say that it's 0.3 up to 0.49 will be seen as weak. Then he also indicated that if you have 0.5 less or equal to our R less or equal to 0.7, we should say that this one is moderate. And then if you look at 0.7 less or equal to R, then less than 1, we say that is large. So you see, the classifications is telling us almost the same thing, but there are a slight variation in terms of the range or the bounds. So this one is saying that 0.1, between 0.1 and 0.29, because less than 0.3 means you are ending up at 0.29. So 0.1 to 0.29 is very weak. Then 0.3 to 0.49 is
Hello, boss.
is 0.49, and in that case you realize that that one can be classified as weak. That is 0.3 to 0.49. Then 0.5 to 0.69 will be considered as moderate. And then we have 0.7 to 0.99 will be considered as large. So assuming that you have a correlation coefficient between two indicators or two numeric values or two quantities, say x and y, and is equal to 0.5. Based on Cohen's 1998 classification, we will look at this one as moderate, that the correlation coefficient here is moderate. This one is a bit slightly different from the classification by the first one that we look at. So if you have negative 0.69, then it falls also within the same moderate. So we say that the correlation coefficient is moderate, but it's negative. This one is moderate, but positive. So you have 0.69 and negative 0.69. They are all moderate, but the difference here is that one is negative and one is positive. So when you are interpreting, it is important that you quote the source, especially when you are writing your dissertation and you're writing for academic purposes. Maybe in exams you can decide to ignore, but if you're able to record them and indicate the classification you're using, it will be good for you. Okay. Now this one shows a graphical representation of a sample, and you see, before you can even look at the correlation, at times it's necessary and good to plot, and when you plot, to give you an indication of what you should expect. For example, if you plot this, you realize that the correlation coefficient here is about if you look at the way it shows you that there's a positive correlation. This one shows that there's a positive correlation, but majority of them are moving away from the line of best fit. The line of best fit is indicated by the red line, and this one is that. So you realize that this one is a negative. If you look at this, it's giving you negative, and this one too is negative. But as the negative, the scatter, as they are scattering wide or they are widely dispersed, you realize that the correlation coefficient reduces. And when they are closer or clustered around a particular point, you realize that the correlation coefficient is high. Now, we say that it is not good to calculate correlation coefficient without plotting the data. So anytime you want to do correlation coefficient, it's also advisable to plot the data so that you know the nature of the correlation. One thing I want you to note is that correlation is not causation. When there's a correlation between two quantities, S and Y, does not mean that S is causing Y to change. For example, if there's a correlation between number of hours you study and your performance, it does not mean that your performance is being caused by the number of hours you study. We see that this association is an indication that there could be some further relationship that we can test, but does not mean that there is a causation. Simple because in causation, we need to determine which one is a dependent variable and which is independent variable. In correlation, we don't know which one is dependent variable and which is independent. All that we see that there is linear association between the two quantities. And you also be very careful when you are dealing with correlation in terms of influential points that are far away, those that are departing from the normal. So because of that, whenever you are dealing with correlation, we need to look at some assumptions, and those assumptions are equal to what we have discussed for parametric. The first aspect is looking at whether the variables are measured on a continuous scale, that is an interval or ratio. Then the second aspect is looking at whether it is normally distributed. So we also need to learn whether our distribution is normally distributed. If it's normally distributed, issues of outliers.
Audio Jungle.